We've seen how single point charges feel a magnetic force when they travel with some velocity v in a region of magnetic field. When we get a group of point charges together, all moving in the same way, we call that a current. If we consider a current flowing in a wire, let's say we're looking just at a section of the wire here, current is flowing from left to right. We have that standard microscopic view of the electrons bouncing around here in the wire. We'll look at an infinitesimal length of the wire, dl. Within this volume now, defined by the length dl and the cross-sectional area of the wire A, there are some number of free electrons in this small volume dV. That volume is the cross-sectional area times dl. Now we'll place a magnetic field in this region. Let's say it's out of the page. And we'll make it uniform. So there are B field vectors coming out of the page everywhere in this region. And we'll note that this is an external B field to distinguish it from the B field that we'll study in chapter 28, which is generated by currents themselves. We'll remind ourselves how much charge, how much free charge is in the volume dV. Well, we know the charge there will be the number of electrons times the charge of each. In another way, you can state this capital N, as we have done before, as the number density times the volume. So that looks like E N A dl. And you'll recall our definition of current. That was N magnitude of the free charge carrier, cross-sectional area times drift speed. Here, drift velocity as a vector of the electrons is opposite the direction of the current flow. Now we can ask, what is the magnetic force on the amount of charge, dq, free charge, moving to the left with velocity vd. You know, on each electron, the force we've studied previously is the charge on 1, it's negative, Vd crossed with B. So the infinitesimal force on dq is going to be the dq charge, drift velocity vector crossed with the B field. Well, look at this expression here. charge times velocity conveniently can be represented in the following way. We have dq, which is E n a dl from above, vd cross B field. This expression here is the current. Here's your volume. What we're going to do is transfer the vector direction here to the dl and define a dl vector which is parallel to the drift velocity vector. So we have that dfb. Now pulling the charge, number density, area, and Vd together, I'll just call that the current. And we have dl crossed with the B field. So this is good for the force on an infinitesimal length of the wire. To obtain the full force on the wire, if that length is L, the force on a wire of length L would just be the integral of this expression. The dl integrates up to the full length. We have our final result here that the force on a length of wire L is IL cross B, where this vector L points along the direction of current flow. And you can see the dimensions of, or the units of the force on a single charge, QVB, which are Coulomb, meter per second, Tesla. That's a Newton. That's for a single charge. For a current, you have the units of current, length, and B field. So that's a Coulomb per second is an amp, the length is meters, and the B field is Tesla. So you can see both of these are consistent, and we have derived the result that we'll use in class, that the force on a length of wire L is the current times this vector, which is the length vector crossed with the magnetic field.